Hi everyone. In today's episode of the Game Math series, we will be discussing vector projection. We'll start by exploring scalar projection and then move on to vector projection. Finally, we'll discuss how to use vector projection to determine a force, showcasing one of the most well-known applications of the dot product. We'll cover both the theory and practical examples in Unity. Now, without further ado, let's get started. Scalar projection is a scalar value, as its name implies. It represents the length of one vector when projected onto another vector, aligned with the direction of the second vector. To make this concept easier to grasp, I've prepared two examples. Let's begin with the one on the left. We have two vectors, A and B. Vector A starts at point A and ends at point C, while vector B starts at point A and ends at point B. The scalar projection of vector A onto vector B is a measure of the length of A in the direction of B. It is a scalar value, not a vector. I will draw a line from point C down to intersect the line segment AB. Let's call the intersection point D. This will help us project A onto B. Now, if we were to project A onto B, we can simply do this. The scalar projection of a vector A in the direction of vector B is the length of the straight line AD, which we will call D. At this point, we are only considering scalar projection, so we will take the magnitude of this vector. Later, when we discuss vector projection, we will use vectors instead of magnitudes. By the way, once we finish with scalar projection, we won't have much work left to understand vector projection, which simply provides a vector rather than a scalar. But let's leave that for later. Scalar projection can be positive, negative, or zero. A positive value indicates that A has a component in the same direction as B. A negative value indicates that A has a component in the opposite direction of B. Zero indicates that A is perpendicular to B. Scalar projection is used in various fields such as physics, engineering, and computer graphics. It helps determine the effective force component along a certain direction, calculate shadows and rendering, and has many other applications. Shortly, we will discuss a common problem in physics and see how we can use scalar projection to solve it. We will also look at a practical implementation in Unity. To sum up, scalar projection is a useful concept for understanding how much of one vector lies in the direction of another. It is particularly useful in physics for decomposing forces, we will see an example shortly, and in computer graphics for calculating lighting and shadows. For instance, if you have ever used OpenGL or any other graphics library to calculate lights and shadows, the scalar projection is commonly represented in these calculations. Regarding our previous example, we can say that the scalar projection of A onto B is the length of the shadow of A on B when a light is shined perpendicular to B. After all that explanation, let's now derive the formula for scalar projection. Let's call this angle theta. From trigonometry, we know that the cosine of an angle is equal to the magnitude, or let me first write the definition. The cosine of an angle in a right triangle is defined as the ratio of the length of the adjacent side to the length of the hypotenuse. This definition applies specifically to right triangles. In our case, the adjacent side is the length of AD, which we are calling D, and the hypotenuse is vector A. But again, since we are talking about scalar, we will take the magnitude of vector A. Now let's rearrange this equation to solve for D. This is the formula for the scalar projection of vector A onto vector B. This formula can be written in terms of the dot product. We can use the geometrical definition of the dot product that we learned in the previous episode when we discussed the dot product to substitute for the cosine here. On the right here, let's write down the geometrical definition of the dot product between the two vectors A and B. The magnitude of vector A multiplied by the magnitude of vector B multiplied by the cosine angle of the two vectors A and B. Since we need to substitute the cosine theta in the first equation, let's rearrange this to isolate the cosine on the left side. So the equation simplifies to the cosine of theta equals the dot product of vectors A and B divided by the magnitudes of both vectors. Now let's take this equation and substitute it into the first one. Let's denote it as equation 1. The magnitude of vector D is equal to the magnitude of vector A multiplied by the result obtained from substituting the cosine theta we just calculated. Since we have the magnitude of A in both the numerator and denominator, we can cancel these factors out to simplify the formula. We end up with the magnitude of vector D equal to the dot product of the two vectors A and b in the numerator and the magnitude of vector b in the denominator. This is the formula for the scalar projection of vector A onto vector b, expressed in terms of the dot product. If you carefully look, we have vector b in the numerator divided by its magnitude in the denominator. This is nothing but b's unit vector, which we learned about in the previous episode. Therefore, we can express this formula as the dot product between vectors A and the unit vector b. If vector b is normalized, which means its magnitude is 1, we can simplify the formula even further as follows. This is because the dot product of two normalized vectors directly gives the cosine of the angle between them, which is the scalar projection in this context. If you noticed in the first example, vector b is aligned with the x-axis. Let me quickly draw the coordinate axis. But in reality, we can project a vector in any direction, not just horizontally along the x-axis or vertically along the y-axis. Now, let's consider the second example. As you can see, vector b is not aligned with the x-axis. It's in a different direction. However, we can follow the same steps we did in the first example without any issues. The beauty of this concept is that we can project a vector onto any direction in space, not just horizontally or vertically aligned directions. So the scalar projection formula simplifies to the dot product between vectors A and B when B is normalized. If B is not normalized, we use the dot product between A and the unit vector B. Let's summarize the different forms of the scalar projection formula we derived. The dot product form, when B is normalized. Cosine angle form, the magnitude of vector A multiplied by the cosine theta, where theta is the angle between vectors A and B. And finally, the unit vector form, when B is not normalized. Now, before we move on to discussing vector projection, let's tackle a mathematical problem together using the scalar projection formula we've learned about. Let me quickly write two vectors with totally arbitrary numbers. Vector A spans 2 units along the x-axis, 3 units along the y-axis, and -1 unit along the z-axis. And vector B, which spans 1 unit along the x-axis, 2 units along the y-axis, and 1 unit along the z-axis. And let's assume that we want to project vector A onto vector B using their given coordinates. Since we do not have the angle between them nor information about whether B is normalized, we can use the formula involving the dot product. This formula calculates the scalar projection by dividing the dot product of A and B by the magnitude of B. Let's start by calculating the dot product first, just like we learned in the previous episode. Two times 1 equals 2, plus 3 times 2 equals 6, plus -1 times 1 equals -1. Adding these together gives us 7. Let's write this result in the numerator. Next, we calculate the magnitude of vector B. Using the Pythagorean theorem, the magnitude of B is found by summing the squares of its components and then taking the square root, as we discussed before. Finally, we divide the dot product result in the numerator by the magnitude of B we calculated in the denominator. This gives us the scalar projection of vector A onto B in the direction of B. By the way, if we had normalized B first, and then calculated the dot product between A and the normalized B, we would also get the same result. You might be curious about how we can apply this concept in game development. Don't worry, we'll soon explore one of its most common applications in physics, and we'll also see an implementation in Unity to gain a better understanding. But first, let's discuss vector projection. Since we've already covered the scalar projection, it should not take us too long. The concept of vector projection involves breaking down a vector into two components, one parallel to a given direction and one perpendicular to it. Geometrically, the vector projection can be visualized as the shadow or projection of vector A when it's dropped onto vector B. It essentially shows how much of the first vector lies in the direction of the second one. I've already outlined the different forms of scalar projection, which we'll use to derive the vector projection formula shortly. In this example, vector A makes an angle of approximately 45 degrees from the x-axis, while vector B spans along the x-axis. As discussed earlier, vector B doesn't necessarily have to align with the x-axis. Just like before, let's try to project vector A onto vector B. The projection of vector A onto another vector B is the component of A in the direction of B. In other words, what we did here is we decomposed A into a component parallel to vector B. This projection represents the x component of the projection. Let's denote it as x. Let me explain this concept to you here on the side. You might recall from high school physics where you were asked to decompose a force into its x and y components. For instance, if you have a force that forms a 45-degree angle with the x-axis, and it lies in the first quadrant, you can find the x component as the magnitude of the force multiplied by the cosine of the 45-degree angle, and the y component as the magnitude of the force multiplied by the sine of the 45-degree angle. This decomposition helps in understanding how much of the force acts along each axis. With vector projection, we're essentially doing the same thing, but using the dot product. The dot product is efficient to calculate, and it allows us to decompose vectors into components along any direction, not just horizontally or vertically. This versatility is key in applications where vectors can act in multiple dimensions or orientations. Okay, now let's start writing the formula for the vector projection. The projection of a vector A onto another vector B, often denoted as follows, represents the component of A that lies in the direction of B. The vector projection of vector A onto vector B is a vector that lies in the direction of B with a magnitude equal to the scalar projection we calculated earlier. So basically we can say that the vector projection is equal to the scalar projection multiplied by a unit vector in the direction of the other vector, which in this case is vector B. To simplify, we can rewrite the scalar projection using the dot product formula. The dot product of the vectors A and B in the numerator, divided by the magnitude of the other vector, multiplied by the B's unit vector. We can write B as follows. So the formula becomes as follows: the dot product of the two vectors A and B in the numerator, and the magnitude of B squared in the denominator. Notice that this is nothing but a scalar quantity, multiplied by the vector B. This is the final vector projection formula. Let me quickly rewrite both the scalar projection and the vector projection formulas in a clearer way, so we can talk about some notes. What we've done so far is project vector A onto B in the direction of B, denoted as x. This is commonly referred to as the parallel projection. Let me quickly write it here. Now, if we want to find the portion of A that lies in the direction orthogonal to B, we can decompose A into two components, x and y, which means we can write it as follows. Remember that we already know A and x is the vector projection of A onto B. The only thing left unknown is y, which represents the component of A that is orthogonal or perpendicular to B. We can simply subtract x from A to get y. This is known as orthogonal projection. Let me quickly write it here. Now let's discuss how we can use vector projection to find a force, which is one of the most common applications of the dot product. A very common problem in physics is where we have to figure out how much force we need to push in the opposite direction of a cart, boulder, or even a car to stop it from rolling down a hill or incline. We will explore two scenarios, each with different information and types of objects. In the first scenario, we will consider a cart weighing 120 kilograms rolling down an incline that is tilted at an angle of 20 degrees. We will assume that the surface of the incline is frictionless. We will solve each scenario using different approaches. In the first scenario, we will simplify the problem by not delving into the detailed analysis of the forces acting on the cart. Instead, we will focus on the amount of force required to push in the opposite direction of the cart's motion down the incline to stop it. This means we only care about the scalar value of the force, not its direction. Therefore, this scenario is a perfect example of using vector projection to find the required stopping force. However, in the second example, we will solve it by analyzing all the forces acting on the boulder, including the friction force. This approach will be more complex, but I will do my best to explain everything clearly. For now, let's focus on the first scenario. In this example, we are dealing with a cart that weighs 120 kilograms rolling down an incline with an angle of inclination of 20 degrees. We assume that the surface of the incline is frictionless, so we can safely omit the force of friction. Since the cart is rolling down the incline in this direction, we can represent the force driving it with an arrow pointing in this direction. Can you guess what force is causing this cart to roll down in this direction? This force is caused by gravity, and it's called the gravitational force, which we draw as a vector pointing downward. By projecting this gravitational force onto the incline, as we learned earlier, we obtain the parallel component of the gravitational force in the direction of the incline. This parallel component is the force causing the cart to roll down. If we know the magnitude of this force, our task is simple. We only need to apply an equal force in the opposite direction to stop the cart from rolling down the hill. The gravitational force acting on the cart is equal to the mass of the object multiplied by the acceleration due to gravity, which is approximately 9.81 meters per second squared. So let me summarize what we need to do. To find the magnitude of the force required to stop the cart, we start with a gravitational force, which can be compared to vector A from our previous example. We need to project this vector onto the incline, similar to projecting vector A onto vector B in our earlier example. This projection gives us the amount of force required to push in the opposite direction to stop the cart from rolling down the hill. This process is exactly the concept of scalar projection. To make things easier, let's express the gravitational force in terms of vector coordinates. The gravitational force is calculated by multiplying the mass of the cart by the acceleration due to gravity. Since this force points downward, the x and z components are 0, leaving only the y component. The y component is equal to minus 120 multiplied by the acceleration of gravity, which is 9.81 meters per second squared. To find the vector representing the incline onto which will project the gravitational force vector, we can construct it simply using the angle of inclination. Since we're only interested in the scalar amount of force needed, we don't need to consider the direction. Let's denote this vector as c, short for cart. We'll use the cosine of the angle for the x component and the sine of the angle for the y component, while leaving the z component as 0. It's important to note that the vector representing the incline's direction isn't the direction we need to push to stop the cart from rolling down the hill. We construct this vector to simplify our calculations because we're only concerned with the magnitude of the force. To determine the correct direction, we already know that we need to push in the opposite direction of the cart's motion. In Unity, where we'll see this shortly, the cart will roll down the hill in the positive z-axis direction. Therefore, to stop the cart, we need to push in the negative z-axis direction. This approach allows us to focus on applying the correct force magnitude without caring for the direction. Great! Now that we have both vectors, we can straightforwardly apply the projection formula to project the gravitational force vector, Fg, onto the incline vector which we denoted as c. This will help us determine the component of the gravitational force along the incline, which is essential for calculating the force needed to stop the cart from rolling down the hill. The projection of the gravitational force onto the incline vector is computed using the dot product of the two vectors divided by the squared magnitude of the incline vector. This result is then multiplied by the incline vector, onto which the projection is performed. Note that the result of this projection is a scalar value, which exactly represents the amount of force we are looking for. I will highlight this scalar value in red. The vector c represents the direction of the incline, but as discussed previously, we are only concerned with its magnitude, not its direction. Let's calculate the final result. Since the x and z components of the gravitational force are 0, the dot product simplifies to the product of the y component of the gravitational force and the y component of the incline vector. This component is equal to minus 120 multiplied by the acceleration due to gravity, which is approximately 9.81 meters per second squared, multiplied by the sine of the angle theta. Since we are interested in magnitude, we take the absolute value of this result. Of course, all of this should be multiplied by the vector c, which represents the direction of the incline. This value x represents the amount of force needed to push in the opposite direction of the cart to stop it from rolling down the hill. It's important to note that this direction depends on the direction the cart rolling in Unity, which we'll see shortly. If you calculate the final result using a calculator, you'll find it's approximately 400 newtons. According to Newton's second law, this corresponds to a mass value of 40 kilograms. This observation highlights that we don't need the full 120 kilograms of mass to stop the cart from rolling down the hill. I hope that I was able to explain this clearly because now we will solve the same question in a more sophisticated way. This solution is more refined because we will solve it as we solve any similar questions in physics. We will start by analyzing all the forces acting on a boulder by drawing a free body diagram. We will use a lot of trigonometry here, so it's helpful if you're comfortable with trigonometric math. Let me remove all these drawings and rewrite this example with a boulder instead of a cart, along with different information. The task remains the same as before. We have to determine the force required to push in the opposite direction of a boulder to stop it from rolling down a hill or incline. In this example, we're dealing with a 1,000 kilograms boulder rolling down a 20-degree incline. Unlike before, we now need to consider friction because it's present on the inclined surface. From the previous example, we established that to stop the boulder, we need to apply a force in the opposite direction of its rolling motion. This force was determined to be the projection of the gravitational force onto the incline, which equals the weight of the boulder. The weight, in this context, is the gravitational force acting on the object, calculated as the product of its mass and the acceleration of gravity, multiplied by the sine of the angle theta. However, if you recall from our earlier discussion on scalar projection formulas, we typically use cosine, not sine. In this example, we'll analyze all the forces acting on the boulder to understand why we're using sine instead of cosine for this calculation. Let's remove all the diagrams and begin by listing all the forces acting on the boulder. We'll include both the forces parallel to the incline, which is the force we're interested in, as well as the forces perpendicular to the incline, even though we don't need the perpendicular components. But this is a great way to learn. This approach will help us analyze all the forces and construct a free body diagram for the boulder object. Let's begin. First, we have the gravitational force, which acts vertically downward as usual. Next, there's the normal force, which is perpendicular to the surface of the incline. Given that the inclined surface is frictional, we also need to account for the frictional force. The friction force always opposes the direction of motion. In this case, it acts against the boulders rolling down the incline, which is essentially the x component of the gravitational force projected onto the incline, as we saw in the previous example. Let's denote the frictional force as Fr. Now, our goal is to find the x component of the gravitational force projected onto the incline. To achieve this, we'll decompose the gravitational force into its x and y components. An easy way to do this is by drawing the x and y axes directly on the boulder. The y-axis will be perpendicular to the incline, and the x-axis will be parallel to it. I'll use different colors to distinguish between them for clarity. When decomposing vectors into x and y components, we always look for right triangles because they are straightforward to handle using the Pythagorean theorem. Let's begin by noting the angles that will aid us. First, the y-axis, which I've drawn as a red line. It's perpendicular to the incline, forming a 90-degree angle with it, as mentioned earlier. Let's illustrate this. Next, if we draw a straight line from the tip of the gravitational force vector to the y-axis, we form a right triangle where we can determine the x component. I'll draw this necessary vector and highlight it in green to emphasize the vector we're interested in finding. If you observe closely, this vector represents the x component of the gravitational force vector, which corresponds to the side directly opposite this vector. Once we find the length of this side, our task will be complete. Currently, we need to determine the angle opposite the right angle in our triangle. This angle is crucial for our solution. Given that the incline is tilted at 20 degrees, and the gravitational force vector forms a 90-degree angle with the x-axis, shown in blue, we have another right angle. The sum of angles in a right triangle is 180 degrees. Since we know the values of two angles, the 90-degree angle and the 20-degree incline angle, the third angle at the top is 70 degrees. Furthermore, the y-axis we drew perpendicular to the incline forms 90-degree angles on both sides. With the top angle determined to be 70 degrees, the angle we need in the small right triangle is 20 degrees. To analyze this small right triangle more clearly, I'll draw it separately here. We have a right triangle where we've identified the 90-degree angle and the angle opposite it, which we found to be 20 degrees. Our focus is on the side opposite this 20-degree angle, which is the value we need to determine. For educational purposes, let's calculate both the x and y components of this triangle. To find the x component, we use the sine of the angle theta, which is the ratio of the side opposite the angle to the hypotenuse. By rearranging this formula to solve for x, we find that the x component equals the gravitational force multiplied by the sine of the angle theta. This explains why we use sine instead of cosine in the previous example. It's important to note that whether we use sine or cosine depends on which component, parallel or perpendicular, we're considering. The angle theta relative to the direction of the force and the incline determines this choice. For the y component, we use cosine theta, which represents the ratio of the adjacent side to the hypotenuse in a right triangle. Rearranging the formula to solve for y, we find that the y component equals the gravitational force multiplied by the cosine of theta. In this context, the y component represents the normal force, but we don't actually need this force for our current problem since we're focused on the parallel component. The force we're interested in is represented by the x component, which equals the gravitational force multiplied by sine theta. This force is exactly what we need to apply in the opposite direction of the green vector shown here. As you can see, this solution mirrors what we found in the previous example. For these types of questions, you could use the simpler first solution. However, I wanted to demonstrate how we analyze forces because real-world scenarios often involve multiple forces acting on an object. In addition to gravity, we also considered friction, which is a valuable learning experience because remember that programming is about problem solving. Taking friction into account, the total force required to stop the boulder from rolling down the hill is equal to the difference between the frictional force and the force we calculated. Let's denote this as F parallel. Let's expand this equation. The frictional force between the boulder and the surface of the hill can be determined. Note that this friction is static friction, meaning it applies when the boulder is at rest, not moving. When the boulder is in motion, we refer to the friction as dynamic friction. We'll explore how to handle these values in Unity soon. The static friction force is calculated as the product of the coefficient of static friction and the perpendicular projection of the gravitational force onto the incline, which corresponds to the y component of the gravitational force. The parallel force is equal to the gravitational force multiplied by sine theta. We can further elaborate on this equation. The perpendicular projection of the gravitational force on the incline, which is the y component of the gravitational force, can be expressed as the mass of the boulder multiplied by the acceleration due to gravity and then multiplied by cosine theta. Similarly, the parallel force can be expressed as the mass of the boulder multiplied by the acceleration due to gravity and then multiplied by sine theta. To ensure the boulder stops effectively, it's crucial that the static friction is significantly higher than the dynamic friction. This prevents the boulder from moving once it comes to a stop. We'll explore how this works in Unity shortly. Let me explain this equation in more details. To correctly determine the net force when considering friction, we need to account for both the direction and magnitude of the forces involved. Here's how it works. If the motion force is greater than the friction force, the object will move in the direction of the motion force. In this case, the net force is calculated by subtracting the friction force from the motion force. If the motion force is less than the friction force, which is the scenario we're interested in when stopping the boulder, we need to ensure the friction force is greater. In Unity, this can be managed using a trigger box to detect when to apply the opposing force to stop the boulder. We'll see this implementation shortly. For a static object, the static friction will balance the motion force, resulting in no movement. The net force will be zero as the static friction cancels out the applied force up to its maximum limit. If the object is already in motion, considering kinetic friction, the net force is the motion force minus the kinetic friction force, but this isn't our current focus. When stopping the boulder, the goal is to ensure the static friction force is sufficient to counteract the gravitational force component driving the boulder down the incline. Therefore, the friction force must be set higher than the motion force to stop the boulder. So the comparison is not just a simple subtraction, but ensuring the static friction force is large enough to counteract the motion force. If this condition is met, the boulder will stop moving. In terms of calculation, we subtract the parallel force from the friction force, as we have already ensured that the friction force is greater than the motion force. Finally, let's talk about the direction of the force we need to apply. In Unity, we will see that the boulder rolls down the hill in the positive z direction, so we need to apply force in the opposite direction. However, after analyzing the forces, we can describe the slope direction using cosine and sine. The gravitational force acts in the third quadrant, meaning both the x and y components are negative. Therefore, the x component is represented by negative sine, and the y component by negative cosine. This detail is not crucial but worth noting. It's important to mention regarding vector projection that all projections must originate from the origin. Since vectors used in our calculations are position independent, we don't need to concern ourselves with this issue. However, when projecting onto planes, line segments, or structures with position, we must first translate them to the origin, perform the projection, and then translate them back. This process can be complex, but for most people and for Unity development, it's generally not necessary to worry about this. If interested, there are plenty of online resources that delve into this topic in greater depth. Let's dive into Unity to explore the implementation of these scenarios. First, we'll look at the cart example discussed in the theoretical part. We have a cart that weighs 120 kilograms. Let me quickly show you this cart. It's simply a cube with two spheres representing the wheels. Additionally, there is a separate game object used to manually set the center of mass on the rigid body component, which helps provide better stability. Now, let's look at the incline. The incline is tilted by 14 degrees, as you can see in the transform properties, where it is rotated 14 degrees around the pitch or the x-axis. It's also important to note that the cart's direction of motion is along the positive z-axis or the forward axis, just as we discussed earlier in the theoretical part. This means that to stop the cart from rolling down the incline, we can apply a force on the negative z-axis. To move the cart forward, I use rigid body forces applied at each wheel's position. Let me quickly show you the code. It's quite simple. As you can see, I apply forces at both the front and rear wheels in the forward direction. I subtract a small offset value from the y component of each wheel's position, so the forces are applied slightly below each wheel. Before discussing the code that handles the projection and applying the force in the opposite direction to stop the cart, let me show how we determine when to apply this force. As mentioned in the theory part, we can use box colliders to trigger the functionality, and that's what we'll do here. Although this isn't the only way, you could bind some input or use any other method. We'll use a trigger box here. Once the cart enters the trigger box, we'll start applying the force we calculated in the theory part in the opposite direction to stop it. Let's hit run and see the result, then we'll look at the code. It's straightforward and based on the calculations from the theory part. Great! As you can see, the cart has stopped. Here, we didn't consider the friction force, and since the cart doesn't roll like a boulder, it stopped immediately. In a moment, we'll see another project with the boulder, where there will be more work to do to completely stop it. In the code, I applied the force in the onTriggerStay method, but this isn't the ideal way to handle forces. It's better to use fixed update, which we'll do in the next example with the boulder. We'll start by expressing the gravitational force in vector coordinates. As we discussed earlier, the gravitational force is calculated by multiplying the mass of the cart by the acceleration due to gravity. To find the vector representing the incline, we can construct it simply using the angle of inclination. As we mentioned earlier, we're only interested in the scalar amount of force needed, so we don't need to consider the direction. We use the cosine of the angle for the x component and the sine of the angle for the y component, while leaving the z component as 0. Finally, to apply the projection, we can use Unity's built-in project method and store the result in a vector called force. You can definitely use the projection formula we derived in the theory part, but there's no need since the project method in Unity accomplishes the same thing. Since this is a vector, it has both magnitude and direction. We'll extract the magnitude by using the magnitude property on the force vector. This gives us the net force magnitude we want. Finally, we simply apply this force at the position of each wheel in the negative z direction to effectively stop the cart. Now let's take a look at the second project. As discussed in the theory part, in this second scenario, we're dealing with a 1,000 kilograms boulder rolling down a 25-degree incline. Unlike the previous example, we need to consider friction because it is present on the inclined surface. Our task remains the same. We have to determine the force required to push in the opposite direction of the boulder to stop it from rolling down the hill or incline. Let me start by showing you the hill. As you can see, it's oriented forward along the z-axis. This is important because in this project, I'll also show you how to determine the slope direction and apply forces in the opposite direction of the slope. As we discussed in the theory part, it's not necessary to calculate this direction since we can simply apply the force in the opposite direction of the object's motion. However, it's a great learning experience. Before diving into that, let's continue exploring the scene setup. You can see the hill is tilted by 25 degrees around the pitch axis. The boulder is also pointing forward, which is its direction of motion. For the rigid body setup, it's straightforward. I've set the mass to 1,000 kilograms, just like in the theory part, and added a bit of both linear and angular drag. Finally, we have the boulder script, which we'll look at in a moment. But first, let's examine the trigger box that will determine when to apply the required force to stop the boulder from rolling down the hill. Let me hit run and show you the result. Great, the boulder has stopped, but you notice that it took a little bit of time to stop completely. This is expected because it takes some time to lose all its momentum. By the way, we will need to apply damping and additional setup to achieve an exact stop on the hill, which we will see in the code shortly. Everything starts when the boulder enters the trigger box. In the onTriggerEnter method, we set a flag to indicate that the boulder has entered the trigger box, and therefore, we can start applying the required force to stop it. We handle this in the fixedUpdate method, as it's better to manage forces in the fixedUpdate method. In the fixedUpdate method, we start by calculating the magnitude of the friction force. As discussed previously, this is the static friction, which is calculated as the product of the coefficient of static friction. We can set and access this coefficient from the physics material applied to the surface of the hill and the boulder. I'll show you how to create the physics material and set both the static and dynamic coefficients in a moment, but for now, let's continue. This coefficient is then multiplied by the perpendicular projection of the gravitational force onto the incline, corresponding to the y component of the gravitational force. Next, we calculate the parallel force, which is equal to the gravitational force multiplied by sine theta, just as we discussed in the theory part. Finally, to determine the net force, or the resultant force magnitude, we subtract the magnitude of the parallel force from the magnitude of the friction force. The stopping force vector represents both the magnitude we just calculated and the direction. Since the boulder's motion direction is along the positive z-axis, we can apply this force in the negative z-axis. I'll also show you how to determine the slope direction and apply this force in its opposite direction shortly. Finally, we apply this force using the add force method. To ensure the boulder stops completely, because in some cases it might still have slight rolling, we can optionally stop all the velocity and also stop the boulder's x-axis rotation, which is the axis of rotation for the boulder once it has stopped. Additionally, we can remove the rotation constraints when necessary. We could also add extra static friction when it stops, but that isn't necessary for our purposes. Now let me show you how we create the physics material and set the static and dynamic coefficients. In the start method, we begin by creating a new instance of a physics material. We proceed to set various properties, starting with static friction, which represents the static coefficient set to 1.35, ensuring it's substantially higher than the dynamic friction, set to 0.6, to prevent the boulder from moving once it stops. Next, we adjust the friction combined property to maximum. This ensures that the highest friction value between colliding materials is applied. Finally, we assign this material to the collider's material property. Now, let's define the slope direction. In the fixedUpdate method, we'll define a new vector 3 to represent the slope direction. This approach is simpler compared to the theoretical explanation earlier. To understand this, visualize the incline from the side view. The x-axis points inward, so we can leave it as 0. For the y-axis, since the incline slopes downward, we set the y component to negative sine theta. Lastly, the z-axis points in its normal forward direction, so we set it as positive cosine theta. I understand this may seem a bit complex. As mentioned earlier, this step isn't strictly necessary. You can always use the opposite direction of the object's motion. Let's test this setup and observe the results. I've added a character that I can control to run away from the boulder, just to add a bit of fun here. Great, the boulder has stopped as expected. That concludes this episode. I hope you've learned something new and found it helpful. Thank you for watching, and see you in the next episode.